present again Professor Jan, who is the co-promoter, is here now. Professor Tarcísio Campos, you can see their names at the bottom. And Professor, it's written Gabriel Bernard, maybe it's the son of Ralph. It's Professor Ralph from the University of. I think you are from the CNEM as well. The president of the Radiopharmaceuticals Institute in Rio de Janeiro. Professor Mauro Valente from the University of Córdoba. Bruno Melo, Dr. Bruno Melo from CDTN as well. Good, Gabriel means half. And Dr. Lucas. Okay, so Balli, let's gonna start it. You have, I already thank you. I'm again thank you all of you to be here, to be part of this committee. And let's Balli have 50 minutes to present what he achieved so far, and then we can discuss about it a little bit. You can start, Balli, whenever you feel good. Good luck.
Thank you, everyone. Good afternoon, first of all, and thank you for joining us for my presentation topic, computational dosimetry of targeted radionuclide therapy and nanotherapy using radioactive nanoparticles. First of all, I would like to thank the committee members and my supervisor, Professor Thelma, and co-supervisor, Professor Yan, for joining today and for all their support. Let's talk about the work. We started working on my PhD project in March 2018. First milestone was the first publication. It was in January 2019. In December 2019, I won a travel grant from Hokkaido University, Japan. In March 2020, we started working with Professor Yan, and now we are here for the qualification. Talking in terms of research production, we got 6 articles published in peer-reviewed journals, and 2 of these articles we have submitted the revision and hopefully waiting for the good answer from the editor. And this highlighted articles related to my PhD project, and we'll be talking about these articles in this presentation. So, since I'm a medical physicist and I deal with radiation therapy, so I must know the aim, and the aim of radiation therapy, where it is given fractionated radiation therapy, is to enhance the dose to the tumor cell and ablate the tumor cells, where at the same time minimizing or having almost no normal tissue toxicities. So basically there are 2 main modes of treatment. First is external beam radiation therapy, and second is targeted radiation therapy. In external beam radiation therapy the external beam radiation therapy is generally used for to deliver curative doses of radiation to the bulb-sized tumor. For example, here it's an example of a lung tumor where the screen shows the uniform distribution of radiation dose. And in this case, the high-energy photon beams or particle therapy is generally used to deliver doses to the deep-seated tumors, and there is generally a uniform dose distribution within the tumor, and the organs at risk are generally saved by adjusting the field size and directions. For example, here in this case, the organs at risk will be heart and spine. They can be either saved by adjusting the direction of the fields or by shielding them with the help of multi-leaf collimators. Second mode is the targeted radiation therapy or targeted radionuclide therapy, in which the radionuclides labeled with the pharmaceuticals are delivered either intravenously or intracavitary or intratumorally depending on the mode, and for example, if there is one bulk disease and there are multiple metastases, so this the carrier molecule, which is the pharmaceutical, generally targets the antigens that are overexpressed by the tumor cells. So on injection, the radiopharmaceutical reaches these tumor sites and irradiate them. However, there is a limitation of this technique, that is generally the bulk tumor, or you can say the solid tumors, generally have a limited blood supply, and they are hypoxic in nature. So due to the limitation of not having the blood vessels, these radiopharmaceuticals couldn't be transported to the different areas of the tumor, which results in non-uniform dose distribution. And in this case, the dose to be delivered to the patient is adjusted based on the organs at risk. For example, bone marrow, and other organs at risk involves the organs through which these radiopharmaceuticals are excreted out of the body. According to the literature, for such cases where there is metastasis and the bulk tumor, the combined external internal radiation therapy can be more effective than using only one type as a treatment modality. So as it can help in better targeting of the metastatic disease, and at the same time it can help to reduce and not increase the tumor dose or radiation dose to the tumor cell, and minimize the normal tissue toxicity. Also, these radionuclides used in this type of radiation emits gamma radiations. So this can be, although it is not preferred that radiopharmaceutical should emit gamma radiation, as it needs radiological protection and other complications. However, still we cannot control, so these gamma radiations can be used for theranostic purposes. There are a number of radiopharmaceuticals that have been approved and regularly used for various diseases, treatment of various diseases. For example, the use of iodine 131 for the treatment of thyroid cancer, hypothyroidism is well known. The use of radium-223 for the treatment of prostate cancer, samarium-153 for bone metastasis is very common, and many more. And there are many radiopharmaceuticals that are under investigation. For example, peptide-based, nanoparticle-based, and antibody-based. There are various radiopharmaceuticals that are being under investigation. So basically, there are two types of radiopharmaceutical, or you can say the carriers that can be used to deliver such therapies. First is where the carrier, one radioactive atom is attached or labeled with one carrier molecule. The carrier molecule can be a peptide, antibody, or aptamer, or anything like nanocarriers. So in this case, only one radioactive atom attached with the one carrier molecule. This kind of therapy is called targeted radionuclide therapy. And this kind of therapy is generally used for the malignancies where low doses of radiation are required. For example, non-Hodgkin lymphoma, and the doses like 15 gray, 20 gray, and higher doses cannot be delivered in this case. The second option is the use of nanocarriers. Some research groups call it the nanobrachytherapy, as it can be used to deliver high doses of radiation to the tumor cell, and similar to the way the seed-based low-dose seed-based brachytherapy does, and it has several advantages, like it doesn't cause, it overcomes several limitations of the seed-based brachytherapy, and at the same time it can deliver high doses of radiation to the tumor cell. and do not stay forever within the patient body. So this is the second type. Now, it's not like these nanocarriers can only be used for radiation therapy. They can be used for imaging as they are labeled or activated with either beta emitters or alpha emitters. So at the same time, these radionuclides emit gamma radiation as well, which can be used for molecular imaging. These nanoparticles can be either also used for delivery of these chemotherapeutic drugs as well, and these nanoparticles can be labeled with several targeting agents like antibodies, ephemer, peptides, etc. And the nanoparticles are available in various forms like polymers, micelles, carbon nanotubes, metallic nanoparticles, and liposomes. And each of these forms has its own advantage. Basically, our work is mainly concerned with the radioactive nanoparticles, and the radioactive nanoparticles can be used in the form of radioimmunotherapy, and radioactive nanoparticles along with and also metallic, they can provide both therapy and radiosensitization, or possibly radio self-absorption can also occur in this case. So let's say it's radiosensitization, and if the radionuclide emits gamma radiation as well as other like particle emission like beta or alpha, then it can provide both therapy and imaging at the same time. So basically, in targeted radiation therapy, we have three main components. One is the antigen that is overexpressed by the tumor cell. Second is the pharmaceutical that targets this antigen, which we call it carrier. And the third is the radionuclide, which is going to do all the work of delivering radiation dose. So a selection of all these three components is very important, but since being as a medical physicist and my work is mainly deal with dosimetry, so I'm more interested in sharing about the selection of radionuclides. So basically we have three choices. One is the audio electron emitter, second is the alpha emitter, and the third is the beta emitters. Audio electrons generally travel a few nanometers and have a LET of 4 to 26 keV per micrometer. So if our carrier molecule is good enough to get internalized by the cell and reach to the cell nucleus, then audio emitters are the best choice. And if we have a single cell or like a micrometastasis, in that case audio electron will be the best choice. In the second case, there is alpha emitters, which can travel few micrometers and have a very high LET. That means they can deliver high doses of radiation with a very low activity to be delivered. So, however, due to the limited availability of these alpha emitters and several other disadvantages, there is a limited use of alpha emitters. The second choice is if we have a bulk disease and it doesn't have a uniform distribution of radionuclide, then beta emitters have a long range, and even if there is a non-uniform distribution of radioactivity, they can be used and they can overcome this non-uniform distribution of radioactivity and can deliver uniform dose to the tumor cells. So now coming about the absorbed dose, how to calculate the absorbed dose. So MUD committee has provided a formalism that can be used to calculate absorbed dose for such therapies. It is from pamphlet 21. So absorbed dose is described as a product of the cumulative activity times the S value, where S value is nothing but the energy deposited in the target volume due to the energy deposited in the target volume due to the activity present in the source volume, divided by the mass of the target volume, that is the absorbed dose per activity inside the target volume. And as we saw, the above formalism is only applicable where there is a uniform distribution of activity. What if, and in most of the cases, there is non-uniform distribution of activity. So there are basically three approaches that are used in such case of dosimetry. One is voxel-based, voxel S-value approach. Second is dose point kernel approach. Both of these are analytical approach that use a mathematical equation to estimate the absorb dose. And the third is the Monte Carlo approach that we are going to that have been is the basis of this PhD project and have been used in our different articles. So first talking about the voxel S-value approach. In this approach, similar to as I discussed, absorbed dose is product of the activity administered, cumulative activity times the S value. So let's say we have two voxels and we have a target voxel is 033 and these two voxels have an activity. So first we'll calculate the S value due to the activity present in 000 in 033 and the second will be the self-absorbed dose. And then we'll individually multiply it with the activity and will sum them. That will give us the absorbed dose. This formalism is very simple to use and very accurate as every geometry can be voxelized. However, this analytical approach do not consider cannot handle the heterogeneities present in the medium, such as air or high dense bone. So that is the limitation. The second approach is the dose point kernel approach, where we consider that point isotropic source is placed at the center of the spherical shells, and energy deposition in these shells is estimated. And then once we have the 1D dose point kernel, and we know the activity distribution within the voxels, we just obtain a 3D dose point kernel using some interpolation techniques, and once we have a 3D kernel, we multiply it with activity and we obtain the absorbed dose in this technique. For instance, let's say we want to estimate the absorbed dose at point voxel R due to the activity present in this volume in different voxels. So let's assume we have a consider voxel R1. So we will first get a 3D point kernel, and then we will multiply it with activity, and then we will with one element, and then we will integrate it over the whole volume. That will give us absorbed dose rate in these cases. So it is very fast, and however it cannot handle the heterogeneities, and it is very biased to the spherical geometries. And implementation of this technique is a bit complicated. The third is the Monte Carlo. So what are the benefits of using Monte Carlo? One is that we can accommodate various kind of phantoms with the Monte Carlo codes within the Monte Carlo codes that can handle the simulation or of the transport of ionizing radiation and calculate those within different mediums, and it can handle the heterogeneities. Other advantages of Monte Carlo are they are very efficient, versatile, accurate, and there is no need for any kind of radiation protection, and we can work with can model the simulation of ionizing radiation transportation. And over the time, there are several Monte Carlo codes have been developed, such as Genford, MCNP6, Penelope, Topaz, XNRC. So once we now we know what is targeted radiation therapy, and we know different modes of dosimetry techniques and how to estimate those. So where are the gaps? First gap is that those point kernel are not only are used for dosimetry purpose, they are also used for in comparing the Monte Carlo codes and checking their applicability for radiation dosimetry. There are many studies on this kind of technique. However, there is no much or almost there is no study as per our knowledge that can tell like how these differences in DPK curves can affect the clinical dosimetry. So we try to work on that. The second gap is the merged cell values are generally used to estimate the therapeutic efficacy of various radionuclides using targeted radionuclide therapy. And for the first time, Fori et al. Presented the radial energy profile using the within the cell if we follow the merge formalism, which says the activities should be uniformly sampled and randomly sampled within the source region. So they considered nucleus as a source region and then estimated the radial energy profile, but author couldn't explain the hump they got in the radial energy profile, so we tried to investigate it. The third gap is that the animal models are generally used to investigate the therapeutic efficacy of various radiation therapies using nanoparticles. However, as you can see, this graph is taken from Elpetier et al. 2017. The tumor volume starts increasing even after, keeps on increasing even after just after the first week of radioactive injection. Well, that's true that there is a tumor control. It doesn't grow as fast as the control group in the case of control group. However, it is still growing, and the activity administered couldn't completely control the tumor growth. So it would be better to have a mathematical model or something that can be very handy and easily used to design better therapeutic or preclinical studies for testing the therapeutic efficacy. So to solve these gaps, we worked in 4 steps. The first work involves estimation of track length of low energy electrons from 1 keV to 50 keV and the SDPK or the dose point kernels, and then using several Monte Carlo codes, and then using this DPK to estimate the absorbed dose for both microscopic and macroscopic scale. The second was we considered electrons ranging from 50 keV to 3 MeV and several beta emitting radionuclides, and tried to test the applicability of several Monte Carlo codes for this kind of dosimetry. So one thing should be noted that I would like to share is that both of these studies were done in collaboration with several collaborators. Like my contribution always remained the XNRC gene for DNA calculations and Topaz calculations. The rest was a Monte Carlo code calculation belongs to the other collaborators. Now coming to the second question. So we performed the microdosimetric calculations for dosimetric calculations for audio emitters, beta and alpha emitters, and also we extended the work of Fori et al. By providing the probability density function. At the fourth step, we performed the in silico dosimetry for low dose brachytherapy using radioactive nanoparticle. We extracted the experimental data from the published in literature, and we used a mathematical model to calculate the cell survival curves. And at the second stage, we used that model to estimate the therapeutic efficacy of several radionuclides by varying the activity, tumor size, and tumor type. So coming to the first step, for calculation of track length, we defined 3 parameters. First was the total track length, or the total displacement of electron, monoenergetic electron within the water, taking water as medium. and the second was R90, the depth at which the electron lose 90% of their energy, and R50, the depth at which the electron lose 50% of their energy. So these were our results that we obtained for the electron range. The results were compared with respect to the NIST database, and as you can see, as it can be seen, that maximum discrepancies up to 50% were observed for low energy electrons, that is 1 keV, and for 5 keV it was around between 5 to 10%, and with the increase in energy, there was the discrepancies were found less than 5%. So moving to R50 and R90, the discrepancies were much less in comparison to the radiation range. The maximum discrepancies were observed for 5, 10, and 15 keV, and other which were although less than 10% or within little higher than 10%. Otherwise, above 15 keV, the differences were generally less than 5%. So, as an application to the displacement, as the electron will displace or travel within the medium, it is going to deposit dose or energy. So in order to get the application, as an application to it, we estimated dose point kernels. So in order to estimate the dose point kernel, we used the following geometry. We placed our detector spherical shells within a big water sphere, and the thickness of the water sphere was 0.025 times the CST range of the monoenergetic electron that is used as a source, and we estimated the energy deposited in each of these shells, and dpk was estimated using this formalism where delta E is the energy deposited in each shell, and delta R is the thickness of each shell, E0 is the initial energy of the electron, and RCST is the CST range of this electron source. So now these were our dpk that we got from our calculations. So maximum discrepancies were observed for 1 keV, 5 keV, and 10 keV. As the energy of electron increased, the discrepancies were reduced within plus minus 3%. So the maximum discrepancies were up to 25 keV, and after that for 50 keV, 100 keV, 500 keV, all the differences were generally within plus minus 3%. And talking about the beta emitters, in that case also the discrepancies were within plus minus 3% in all cases. So as an application, discussed about the dosimetry using dose point kernel. We estimated dose rates using our calculated dose point kernels from using several Monte Carlo codes, obtained using several Monte Carlo codes. In order to obtain the dose distribution, we need activity distribution and the 3D kernel. So we can obtain 3D kernel from 1D kernel by 3D cubic spline interpolation that was done by Professor Mauro and his team. And we considered two activity distribution. One was a microscopic scale distribution where the voxel number was 121 into 121 into 1286, and the voxel cubic side was our range of CST range time divided by 40. So the voxels were divided by into 40 voxels basically, and the voxels were activated in such a way that initially the first voxel was activated and then the voxels were activated in pair, and the distance between the voxel was increased as we went along the z-axis. So for the second model, that is macroscopic scale, We used the standard nuclear medicine calibration phantom as here, and for this distribution, the voxel size was 1 millimeter cube. So once we had a 3D kernel using from 1D kernel using cubic spline interpolation, this is an example we have obtained using for Penelope 50 kV electron source. Once we had all the dose rates obtained, dose rate distributions obtained, we need to compare them, and in order to compare them, we use gamma index formalism that has been that is widely used in radiation therapy for radiation plan comparisons. So in gamma index defined by Low et al., there are two parameters. One is dose to distance agreement, and the second is dose difference. Here is called difference in dose rates. So for dose to distance agreement, we considered the tolerance of RCSDA by 40 for microscopic scale and 1 millimeter for macroscopic scale, and dose rate difference was kept 1% in each case. So these were the dose rate, absorbed dose rate profiles that we obtained for several various electrons. This was for 5 keV, this is for 10, and say one thing to note is that the maximum discrepancies were obtained between the absorbed dose rate profile was obtained for low energy electron. As the energy of the electron increased, the absorbed dose rate differences were much less. So this was observed in the gamma analysis as well. For 5 kV, the discrepancies were, or the differences, there was only 65 or 60% voxels on average passed the gamma analysis test, whereas for 50 kV, about 90% of the voxels passed this test. On coming to macroscopic scale, almost all the absorbed dose rate profiles completely overlapped each other, no matter whether it's a high energy or low energy electron. And the same was observed for in the gamma analysis test, that 99% of the voxels passed this test. Now coming to the second part, that or the second gap, that is the calculation of radial energy profile and the estimation of cellular S values. We consider several beta, Auger, and alpha emitters. So this was the cell geometry that we considered, and this was for DNA, and this is from XNRC. So the radius of the nucleus was 4 micrometer, and the radius of cell was 5 micrometer, and this blue area that has the radius of 1.2 times the radius of the cell acted as the surrounding. So as I discussed before, that the mud formalism considers the uniform distribution of radiation within the source region. So in order to do that, we have to come up with a probability density function that can sample points uniformly within the shell or spherical volume. So to do that, we got a normalized probability density function. We solved separately for r theta and phi from the volume element, that is for the spherical coordinate system. And on solving those equations, we came up with three equations where for considering a spherical shell with the r minimum as the inner radius, r maximum as the outer radius of the shell, and by implementing these equations, we can sample points randomly and uniformly within a spherical shells or spherical volume, where r, theta, and phi are the coordinates of the spherical coordinate system. Chi1, chi2, chi3 are random numbers. Using the above details that I discussed, we obtained our energy, radial energy profile, and compared it with Qualify et al. Results. So we found that the the radial energy profile reported by Foray et al. Shows that more energy is deposited near the cell center. That means more points are sampled near the cell center instead of getting uniformly sampled. Or other possibility is that authors reported something else that is not radial energy deposition. So this makes sense actually, this triangular curve, because let's say if we divide this 0 to 4 micrometer into 40 shells, and each shell has a constant thickness, then as we go from 0 to 4 micrometer, the radius of the shells increases. That means that there is more area to, or more volume to sample, more points. More points means more deposition of energy. So if we have a uniform and randomly sample the points within the spherical shell, one should get the triangular energy deposition curve. So, and also one point I would like to state here is that we also compared the S value reported by the authors in their paper. So the differences in the S value were within 5% to 10% deviation. So that means that if same number of points are sampled within a particular volume, they are going to deposit same mean dose as S value represents the mean absorbed dose per activity. So these sampling of points doesn't show difference when you calculate the S value, but it comes up when you see the energy deposition curves. So now coming to, we also investigated the impact of emission spectra on cellular S value. To do that, we chose two radionuclides, technetium 99M and indium 111. And we used the emission spectra published by Ball et al. And used it as an input to both GN4DNA and XNRC, and compared our results with Seppel et al., which used the same input spectrum. And the discrepancies were less than 5% in most of the cases, at least with the first three cases. In the last two cases, the discrepancies were around 10% and even higher than 10%, that is 20%, 25%. These discrepancies can be attributed to the limited knowledge of the cell surface thickness that was used by Seppel et al. So that was the cause. Otherwise, the discrepancies were found less than 5%. That means if the same input spectra is used, both the GN4 and XNRC give consistent results. On coming to the Auger emitter and alpha emitter, these S values were calculated. To calculate these S values, we simulated the decay of radionuclides using the internal modules of these Monte Carlo codes. For example, there is a radioactive decay module or class in GN4 that can simulate the decay of radionuclide, and XNRC particularly takes in the files extracted from NNTC website, and which there is a class that can simulate the decay of radionuclide by using the ENSTF files from extracted from NNTC. Important things to note is, first thing is that GN4 DNA accurately simulates the decay of alpha emitters, as the S values calculated using merge cell software and the GN4 DNA, they deviated less than 10% in all the cases. Whereas for Auger emitters, we even got deviation as high as 48%, which can be because of discrepancies in simulation of radioactive decay. And another thing to note is the magnitude of S value. The alpha emitters deposit almost 30 times more absorbed dose within the cell in comparison to the Auger emitters. On coming to low beta and high beta emitters, the same thing was observed, the deviation higher than up to deviation up to 40% or higher, and which shows the discrepancies in modeling of the decay of different radionuclides, and the low beta emitter deposit almost same absorb dose as OJ emitters. On coming to the high and beta, low and high, medium and high beta, they deposit almost negligible or very less dose in comparison to the OJ and alpha emitters. On coming to the radial energy profiles, we proposed to estimate profiles by normalizing this energy deposited profile by the square of the shell radius. So if we normalize the energy deposited per decay by the square of the radius of the shell, we get flat flight profiles for OJ emitter, which actually represent the properties of OJ emitter, as we say that even literature reports that OJ emitters travel nanometer distance. So ideally they deposit all their dose within the source region. So let's say if we have a nucleus as source, so everything is deposited within the nucleus, and there is sharp dose fall or energy. There is almost zero energy deposited within the other the region contains next to the source region. Whereas as the energy of the emitted electron increases, like in the case of low beta, high and medium beta, so the more and more energy gets transported out of the source region and is deposited out, which actually shows the crossfire effect of the beta emitters. Now coming to the last part of our work, that is calculation of survival fraction, we actually use the mathematical formalism provided or proposed by Seffel et al., which considers two parameters. One is first it assumes that survival fraction curves are can be considered as exponentially decreasing function of dose in the absence of proliferation for low dose treatment. The second exemption is that the tumor grows at the rate of lambda along the course of treatment. The third is that the uptake and washout rate of nanoparticle is exponential, which is represented by m and k, and this equation can be used to estimate the cell survival curve as a function of time. So there are three main parameters that one should know to estimate the cell survival curve. One is the extrapolated dose rate, that is the dose rate at time 0. One is uptake rate, washout rate. TI is the day or the time of injection, whether it's in hours or days or weeks. And the second is when the tumor was measured before injecting the radionuclide. So based on this, we estimated each of them. For instance, this purple shows the data that I extracted from Cathy et al. So they had the data for 30 minutes, 1 hour, 4 hour, 12 hour, and 24 hours. So I put it there, and then I used this mono-exponential function to plot and try to find which plot matches best. And it was nothing but a hit and trial, and based on this, I got my value of m and k, that is uptake and washout rate constants. And once I had that, I needed how the tumor grows or tumor growth rate. For that, we every experimental or preclinical study report the growth curve for control group. So I digitized it and tried to get the best fit using the least square fit method, and I got my value of lambda. Once we had k, m, and lambda, we need the extrapolated dose rate, which is nothing but similar to Merck formalism. If we consider the tumor is a spherical, is a sphere, and the radioactivity is uniformly sampled in it, So we have the administered activity value, and we have the absorbed dose per activity. And once we know how much activity was retained within the tumor, and then we have the cumulative activity, and this FT is the mass fraction, which is basically used when in the case when the tumor and the target organ are completely not the same. Like for example, if we are considering the case where tumor is present within the lung, so in that case the tumor, we will consider the mass of the tumor divided by the mass of the organ, total organ divided plus the mass of the tumor. It's just basically to give a fraction, how much fraction mass of the tumor is present within the organ. And once we have the cell survival curve as a function of time, we can get the volume curve, time volume curve of the tumor by just multiplying the initial volume with the cell survival fraction. So now the last part is how we estimate the efficiency of such treatments. So which is generally done by defining a parameter, that is minimum survival fraction, which relates to the time where the cell killing, tumor cell killing, and the cell growth of tumor cells is balanced. So it can, that is called critical time. Critical time can be obtained by taking a time derivative of survival fraction equation and equating it to 0 and solving for time t. And basically critical time, as I said, represents the time less than critical time is the time when cell killing is happens more than the proliferation. Whereas in the second case is the case where proliferation overtakes the cell killing. So this graph shows this situation. For as it can be seen, this is the minimum of this curve, and this time relating to this point will be called the critical time, and the survival fraction will be called the minimum survival fraction. And after that, there is a steep increase in the survival fraction, which is because now the radionuclei is ineffective. Kill of the tumor, the rate of killing of tumor cell is very less in comparison to proliferation. So these were the survival curves that we calculated. Like here, it's blue represents the curve that we estimated, and the red is the experimental data. If you see the overall trend of all our calculated results match with the experimental trend. However, the discrepancies like this, there is sharp fall in the tumor volume. It may be because it is not visible in experimental results. Our hypothesis is that the tumor architecture takes some time to reveal the differences or decrease in the size of the tumor, whereas our mathematical models do not consider or is not that sophisticated. That's why we see the rapid fall, and then there is the same trend as the experimental. And the more the discrepancies can be attributed to the large standard deviation. And for example, in this Merriam et al., they used the palladium-103 radioactive nanoparticles coated with gold. So in that case, the platinum emits low energy X-rays, which can lead to radiosensitization, so which means more dose deposits or more cell killing. Or other possibility is the self-absorption, that whatever radiation is emitted is getting absorbed. So which may lead to the discrepancies, and we haven't considered that in our calculation. We hopefully will consider it in future studies or maybe a PhD. And the best curve we got, agreement we got was for Wangela. They used the carbon nanotubes, and hence there was no possibility of radiosensitization or self-absorption. And So we believe that one factor can be radiosensitization, self-absorption, and another is the standard deviation available. And also there was limited pharmacokinetic data available in literature. Like they don't provide too much data. It's only like 4 or 5 points, which limits the accuracy of uptake rate and washout rate. So if we have a better pharmacokinetic data, we can get better results. Now, in order to estimate the therapeutic efficacy of three radionuclides, particularly platinum-103, samarium-153, and gold-198, one is Auger emitter, one is low beta emitter, and gold is high beta emitter. We considered three cases. In the first case, we kept the tumor size constant, growth rate, and radiosensitivity constant, uptake and washout rate constant, and just varied the radioactivity, and this is what we got. For platinum, we got that as we increase the radioactivity, the activity, administered activity, there is a decrease in the critical time, and there is increase in the critical time and decrease in the survival criteria. So that means a higher activity of platinum-103 can effectively ablate the tumor cells that we considered here. And whereas in the case of samarium and gold-198, all radioactivities administered activities were effective. So that means even the low activities of gold and samarium can effectively treat tumors of the size 0.3 cc if they are from PC3 or similar cell type. Now the second and third case considered. In the second case, we considered constant tumor volume, but the activity deposited by these radionuclides was constant. So we need to fix the radioactivity of the one radionuclide and calculate the required radioactivity of other radionuclides, and then we estimated the cell survival curves. The condition here was constant absorbed dose deposited by all radionuclides, but variable tumor volume. In the third case, we had a variable cell type, and the absorbed dose by all radionuclides was considered constant. So this is the case here. We considered platinum radioactivity of 60 megabecquerel, and we varied the tumor volume from 0.3 cc to 1 cc, and it was observed that as the tumor volume increased, there was increase in the cell survival and decrease in the critical time. And it was also observed that almost 600 times less radioactivity of gold-198 and samarium-153 is required to deposit same absorbed dose as that of platinum. In the case of variable cell type, like B16F10 is a very aggressive, rapidly growing tumor cells they are also radio resistant as well. So in order to we got these curves and we used the platinum administered activity of 600 megabecquerel. So we found that for PC3 600 megabecquerel activity of platinum can effectively treat it, whereas for B16F10 the critical time was 10 days, and after that cell proliferation overtook the cell killing. So in conclusion, we got that the calculated electron track length, DPK, and 3D convolution absorbed dose showed the estimated absorbed dose showed that all Monte Carlo codes can be used for are suitable for this kind of dosimetry. However, the differences are only observed in the microscopic scale, not the clinical scale, where we use voxels of millimeter-sized voxels for our day-to-day dosimetry. Second thing was that to compare the accuracy of Monte Carlo codes, one must use monoenergetic sources instead of using the emission spectrum of various Monte Carlo radionuclides, as these emission spectrums lead to smoother differences and smoother results in high-tech differences. And other we found concluded that very well-validated emission spectrums must be used in estimation of S values, and the internal modules that are used to simulate the decay of radionuclide must be used with care. Also, we found that concluded that possibly either Fourier et al. Used wrong normalized the probability density function, or they reported something else that is either absorbed dose, or which is should not be the radial energy deposition. Other thing we found concluded that the mathematical model proposed by Seffel et al. Is very can calculate the cell survival curves or reproduce the experimental results to the great extent, but better knowledge of uptake rate, washout rates, radiosensitivity, growth rate of tumors is very important for this calculation. And we concluded that with low radioactivities, gold-198 and samarium-153 can effectively treat large radio-resistant and aggressive tumors, whereas for platinum, it is only is able to treat effectively the tumors, millimeter-sized tumors. Our future work, our remaining work, you can say, is we are planning to perform our targeted radiation therapy dosimetry on realistic phantom. For that, we have segmented the DICOM images of a patient with prostate cancer, and we have segmented each and every important organ at risk and the target volume. And we also wrote a C++ script that reads this phantom and converts into the file that is suitable for voxelized human phantom library of XNRC. And we are working with the team of Professor Yan on validation of independent reaction time technique that is generally used to simulate the radiolysis of water, and it's really very fast and is suitable for small systems, and it's much better, faster in comparison to the general Monte Carlo approach that is relevant in Gen 4 DNA right now. And we have investigated the impact of different scavengers on radiolysis of water. I have finished the validation. I have to write the article on it, and final will be to write the thesis and the phantom. This is the phantom that I was talking about. We have segmented it, and we have ran the case. In this case, Bruno is working with me, and we are working together. He has helped me a lot. And these are the DVH curves that we obtained for the test case, which clearly shows that targeted radionuclide therapy using nanoparticle is really effective, and it saves organ tissues to a great extent. This is our future work plan. So I have my PhD scholarship till March 22. We'll try to finish things a bit earlier, but that's the problem. And what can be done in future, what the other guys can do is one can study the radiosensitization or self-absorption that occurs in the case of high-Z nanoparticle used for treatment of like in nanobrachytherapy. One can extend the work of Seffel et al. By including quadratic component of dose and the cell repair, considering the cell repair as well. And since the interaction of radiation and the cell repair is stochastic, so it is also be interesting to take the whole mathematical formalism to the Monte Carlo scale. And also, as we saw that the emission spectrum makes it really complicated to perform these dosimetry. So it is much better to come up with a better solution that can be used and that can provide better, accurate emission spectrum, or at least tell us what are the discrepancies and how it can result in a affect our or impact have impact on our dosimetry. And the last is the cell model that we used is just is not do not match in any case with reality. So one can take the image of the tumor cell, they can be segmented and used for dosimetry purposes. That will represent the more realistic view of the what happens inside the tumor. Thanks for your attention.
Okay, very good, Kali. It took a little bit longer than we expected after all we trained.
How much I took?
58, but that's fine.
Oh, I'm sorry. I tried to get. I got too much. I was not expecting to. I explain these things, but I thought no one is interrupting. That means I have time.
Don't worry. Yeah, don't worry. So here, if let's go for the discussion. So I thought maybe we have different institute from this international committee. So we thought maybe to have for the more external to the closest institute distance in terms of institute distance. So I would invite Dr. Tiago, who is the more external and is far from us, and then you can make your points, Tiago, in terms of the manuscript that you've read, and in terms of the presentation that Balli gave. So you'll be free, and there is no time to finish it. It's just what do you think is needed to talk about. Thank you for coming.
Okay.
Yes.
Okay. No. Thank you for the invitation. Thank you, Balli. I think you did a great job. There is a lot of work there. I think and it's a lot of very good quality work. I will mostly comment. I'll comment on both the presentation, what you showed on the presentation, and also what I saw on the thesis. I do apologize, maybe if there is a little bit of difference in terms of like target expectations coming from me and what is expected by the UFMG, but we can just chart. As I said, I think like that the work that you've done is great. I think is very well explained, very well discussed. The first point that I would like to or the first suggestions or comment I have in terms of what you wrote on the manuscript is that the impression I got is I could see you had a lot of publications, but from the introduction part of your manuscript is that was still a little bit open in terms of what are the topics that you were looking for, what are the novelty of your PhD. I think like that you should try to highlight a bit more. The way you did on the presentation, I found much better than on the written document. And now also concerning the presentation, the document, I think I'll probably send to you my written comments by email. I think like it's much better rather than me going through point by point. The one general comment that I have to you is try to have a bit more consistency, both in terms of the writing, the knowledge that you use for writing. I found that like several parts of the document, they are written in a different way. And the last point concerning the document is try to highlight your findings. I know that like that a lot of these publications are group work, as you described very well, that like that you were more involved with some of the Monte Carlo codes, not with all of them, which I completely understand. It's impossible for you to get to know all the codes. But I think like in terms of the thesis, at least what was always asked for me was that you should, for your thesis, you should highlight your achievements, not the group achievement, but your achievement. What was the what are the things that you've done, and basically highlight your findings. Like I said before, I think like that in terms of the material, you have a lot of work, you have a lot of publication. There is a lot of things for you to write about, which is fantastic. It's much harder when you have presentations where you don't have the material to write. In your case, it's the opposite. You have a lot, just highlight your achievements. Okay. Now, in terms of the like one or two specific points that I found, you did mention the three aspects of the three aspects of the radiopharmaceutical, that you have the radioisotope, you have the pharmaceutical part, and you have the delivery mechanism. And the one thing that like I would like you to explain it maybe a little bit better is because you did say that like on your documents that the optimal half-life for these are below a given amount of days, and but I couldn't understand from your presentation is that what justified that statement.
Well, Professor, depends on it's basically the half-life depends on what we call about half-life is the two things. First, whether the radionuclide is inside the body of the patient or it's in the shelf. If it is the shelf, then it should be long enough that we can keep it in the storage. Reasonable will be like 10 days is the maximum, I would say. And when it gets inside the body of the patient, then the half-life is totally controlled by the biomolecule or the carrier molecule that is attached, and how its chemistry works and how it is excreted out of the body. So my main concern about when writing about the half-life was that it should have enough half-life that it can be used more times, or it should be like practical to use. It should not be like you generate it the same day and the same time and you have to deliver and it's going to decay within a few hours. So that was my point in writing there, and that's
okay. Okay, and the other point that if you could explain, because I saw that like that at this stage you're mostly comparing the different energy of the particles, and the basically the expectations of different Monte Carlo codes in terms of the final dosimetry. One of your conclusions was that that perhaps to be a fair assessment of this comparison, you should use the monoenergetic of emission rather than the spectrum, because I think like if I'm correct, you did mention that that there is some sort of I can't remember now like the term that you did used, but my question is that do you think that going from because you just said that like you needed to improve your environment in terms of the cell geometry, but why do you think that like in terms of the physics aspects of the emission you are going to a more simplistic approach?
Well, Professor, I agree with your point, and to what I understand is, you mean like in the reality, what we do is we don't deliver to the patient monoenergetic electron. More realistic is the radiopharmaceutical. So why not to compare their accuracy with the radiopharmaceutical emission spectra instead of using monoenergetic? Well, Professor, the thing is, when we use emission spectra, it smooths the result. Like there are many emission probabilities and different energies, so we are not able to see what exactly is missing. For instance, I showed the DPK curves that we got for 1 kV. They were totally very varying, as you can see here. This is if we use the emission spectra, so we won't be able to find the difference accurately. Like in this case, we couldn't find all the differences were normalized to plus minus 3%. But when we did the comparison for like 50 kV to 3 MeV, we actually there is a MCNP formalism that was not done by me. It was done by Bruno, and his formalism were very deviating from the in terms of DPK for 50 kV to 3 MeV range, whereas this difference was not visible in the pharmaceutical emission spectrum. So that's why we concluded this point, and that one should use monoenergetic electrons to estimate the discrepancies between the Monte Carlo codes instead of using the emission spectrum, because they hide the differences between the Monte Carlo codes.
No, I understood that. Like my question was also based on these assumptions that you just said, that like that by using the spectrum you have like this smoothing effect. Why do you? What do you think would be achieved by having like a more improved geometry description on these evaluations?
Well, Professor, there is only, as per I know, there is only one study that is from Incerti group from France. They have used a realistic cell model to model the energy distributions for realistic cell model, and they, I think, used iodine 125 as a target, as a source. And according to their findings, they found that results will be much better. They report that it is much better to use the realistic cell models. However, they don't show still the complete reality. They only show the one phase of the cell. However, the human body is continuously changing, and the cells are continuously changing their stages, cell stages, and so the radioactivity distribution may vary. And I have some images from that group of the cell, and we were planning to perform such dosimetry and see what's happening, but probably I'll be doing after this PhD, or maybe later, some other time.
Okay, and now just a little bit more in terms of your findings, the work that you did by comparing with the results from the full year group for the energy deposited along the radius. You did describe some. You did describe like your assumptions. Is more like a curiosity, because basically their result looks almost like if it is if you sum the area of the curve for both, did you see if you have like the same mean value or not?
Well, Professor, I have the results for S value that I have compared, but this idea of calculating the area below the surface, below the curves, didn't came to my mind, but I can check it. Like if the area below the curve for both cases is same or not, but yes, the mean absorbed dose in both cases that I calculated using gene for DNA is same. Actually, their paper describe. I used the same physics as they used in their paper. I used the same Monte Carlo code, that is gene for DNA, that they used, and everything, all setup was same. Only thing was I couldn't replicate with my the probability density function that I came up with. So that's why we assume that either this quantity is not the energy deposition, or the probability function they use is little bit different than what we use.
Okay. I think like from my side, that's it, Thelma. Like I said, I have made some notes in the document on the thesis, or on the thesis, I don't know how you call itself, and then I'm happy to share with you and with Bungie my findings or my notes.
Thank you, Dr. Thiago, for your comments and for your giving us time. Thank you very much. We appreciate it.
Good. Tiago, you can send the manuscript as soon as you feel free for it. We will consider all the points that you have noted there. Okay?
Okay.
Yes, okay. Let's then, many thanks again, Tiago. And let's go for Professor Mauro Valente from Argentina. Yes, please, Professor Mauro.
Hi again.
Hello, Professor Mauro.
A very good presentation. I may start saying that I agree with a lot of comments already mentioned by Thiago, so he has already said a lot of things that I was considering. But I would like to say, just to starting the feedback, that I have understand your document as somehow some kind of support material. So I didn't review it as a preliminary thesis, because of course it's not presented as a PhD thesis. It's some kind of supporting material for the presentation you have today. So I have just 5 specific issues that I would like to share with you in order to interpret your presentation. I would like to ask about when you were working with the Auxiliary electrons, what were the absorption energy you have implemented in the simulation? Because of course the electrons have very low energy, and then the absorption value may impact not negatively in the final results. Do you remember about the absorption energy implemented during the simulation of electrons?
Sorry, Professor Mauro. Actually, I'm not able to hear clearly your questions. Maybe there is a echo or some kind of thing. Can you please repeat the question?
I would like to. I will try to formulate it again. I was wondering about what was the absorption energy you have implemented in the multi-cloud simulation for the Auxiliary electrons.
It is 7 electron volts, Professor. I used gene for DNA to get these radial energy profiles, and I used the 7 electron volts as the energy cutoff. That is the minimum that we can use.
It's a pretty nice low value. So results shouldn't be affected by the absorption energy.
And also, Professor Mauro, one thing that this was also, we got the question from the reviewer as well about this, the energy cutoff. The thing is that even if we use 1 kV as a cutoff, then it doesn't make a difference, because what we are using is the cell model that is in micrometer dimension, and the total range of 1 kV electron is 1 nanometer. So it is not going to affect our results in any way, even if we use 1 kV as a cutoff.
About the cell model, I have also a question in the following issues. Okay, thank you very much for clarifying about the absorption energy. So, go on. I would like to ask you about when you have simulated the alpha particles. Have you used the GM4?
Yes, because XNRC doesn't support alpha emitter emission, so I only use Gen4 in this calculation, Gen4 DNA, and these are the results. And
do you remember if the GM4 is able to perform ion transport?
ion transport, yes, it supports all the ion transports, and I think we have mentioned it in our manuscript, but I don't verbally remember all the type. But yes, it supports maximum all type of ion supports. Ion transport.
About the primary and the fragment sequence?
Sorry, Professor, I couldn't hear.
That if you remember that GM4 have performed the full ion transport for both the primary particles as well as the nuclear fragments.
We try to simulate the complete decay, and we consider the complete transport of these ions in our simulation. So I believe since we are getting the consistent results with the mud cell, we assume that transportation by Gen4 DNA is perfectly fine for the ions and the fragments as well.
If I may, Professor Mauro, maybe did you change? I think would be like if he changed anything on the physical parameters when he simulate with Gen4.
Just inherent to the code, because some of the codes are capable of performing the transport and others just take the deliver the energy.
Yeah.
And in such code, it is not possible to distinguish between the all different physical situations. And so I would like to be sure that the project have taken into account.
Yes. Okay.
About 60 that it was, so there is no problem. It's a good job. I have already taken down this next issue, and it was related to the cell model of core. I guess that the cell model should be key and mainly because there are some quite solid constituents within the nucleus, and that, in my opinion, is the reason of having so different behavior between these results and the result produced from the back because the more solid constituents really have higher stopping powers, and that's the reason for that differences. And the areas below the curve, of course, as Thiago pointed out, they should be quite more the same value because they represent the values.
I agree with you, Professor Mauro, about the cell structure and realistic models, and we'll try to consider it in our future studies. And as I mentioned, we have the models, and we'll probably maybe during next year or maybe after PhD, we'll consider and work on that as well.
So I have just a final question, which represents for me the more relevant ones, and is I couldn't interpret clearly because I was not capable, but I understand from Thiago's questions that was maybe perhaps the same for him, so I will formulate this question. Could you please state your thesis specifically, because there is a lot of very interesting work. That's not the point.
Yeah,
you should present exactly in your thesis what are you supposing to investigate your thesis.
So, Professor Mauro, the basic plan was first to check how the genes for the, like I use genes for DNA, XNRC, and Topaz for my work. So and that's the only codes I know, and my aim was first to know how much variation it behaves, because there is no experimental data at low energy. So the only possible way to know is by comparing Monte Carlo codes. So first the idea was to compare the Monte Carlo codes and know which one is accurate and how much is accurate, and what happens if we use small dimensions or large dimensions. Once we got the accuracy, the results, then idea was to perform some therapeutic efficacy studies for various radionuclides that are used in these kind of targeted therapies. And the last moment, the end point of my study was to, once we had that okay, these Monte Carlo codes are suitable to perform the calculation, and yes, once we have got the dosimetry at the cellular level, our idea was to apply it, and somewhere there it can be really get fixed. Like I calculated the therapeutic cell survival curves for radioactive nanoparticle studies. So the highlight of my work is the cell survival curves that I performed recently, and hopefully if we get published, that will be the real core, or you can say the real meat of my work. And earlier was the supporting that grows a story line that yes, this is accurate, this step. These were the small steps, but the main step is the cell survival curves and the therapeutic efficacy that we calculated for the three radionuclei. One is Auger emitter, another is low beta and high beta.
Okay, so just as a suggestion, from my point of view, clearly you have a lot of very interesting issues. You have already investigated a lot of them. You have a lot of part of the puzzle, but you need to put it together. So there is really useful, or it could be really useful if you could be able to formulate just one or at least two sentences establishing what is your thesis. And thereby you will be very, you will find a very practical way to organize the rest of the work you have already performed. I am still planning to carry out an extra work. So, but it will be very useful to you to specify very clearly what is your postulate, what issues are fundamental that you're looking for. It would be useful also to understand what are your specific personal contributions, as Thiago said. This should be really mandatory to be stated as initially.
Sure, Professor Mauro, I apologize for that. Actually, it was my...
that was the preliminary document for supporting material. That's clear for me. Just as a suggestion, you have already a lot of time, at least 2 years, 1 year and a half at least, so you can elaborate and formulate a very nice thesis.
Sure, Professor Mauro, I will work on it. Thank you very much for your suggestion. And I'm really sorry I couldn't do it, maybe because of inexperience of writing thesis, but surely I'll improve it.
Okay. That's all in my opinion. Just congratulations to you and of course to your advisors, because you have performed at the time a very interesting work on with a lot of originality and personal contribution. So congratulations from you and all the team.
Thank you, Professor.
Thank you,
And
Professor
thank you for your
Mauro.
time.
Good, very good points. And if you have any notes on the manuscript, you can also send us. We will take care
Okay.
of all your notes. This is important as well. It's this was a huge point to discuss with Bali. What exactly you did and what is the collaboration group did. We were discussed about that this morning still. So it's a good point. We have to put it separate. And also, what about Tiago said, the achievements. What was the main achievement and the novelty? What is new? What did you bring that is new? This is really important. We hope in the next version of the thesis, the final version, we will have all these things written in a better format, I think. Many thanks.
Many thanks, Professor Mauro.
Let's invite them, Professor Half. You can point out your questions or any suggestion or anything.
Hello. Hello, Bali.
Hello.
Professor Half.
Hello. So, I will. It's just a few questions. It's not questions at all. Some are questions because I was in doubt during your presentation, but some are more like tips to get your thesis better, but just tips you can accept or not. It's with you and your both course supervisors, okay? So in the topic 1-to-1, the radio labeling nanocarrier, okay, of your thesis, and of course I am a radio pharmacist. This is my point, okay? So you have described the whole process of introduce a radioactive material or a radioisotope in your nanoparticle, okay? But the main process that happens when you have to put something in a nanoparticles is or physisorption or chemosorption, okay? And a main point that you have discussing in all the radiopharmacy area, of course, is the amount of radioisotope that you can put in the nanoparticle, okay? Put a radioisotope in a nanoparticle is very easy as well. The chemistry of the radioactive material is very easy, but we need a molecular amount of radioisotope to really have a therapeutical effect. So I really think that in this paragraph that you have a very long introduction, and I really think that you should focus your radio labeling in chemisorption and physisorption aspects only, okay? And give at least one paragraph on the molecular amount of radioisotope linked, labeled with your nanoparticle, because this is the main point for us that work there in the hospital with a patient, and for us that you have to radio labeling a kit to inject in a patient. So this is the main point, and I really think that's missing in your introduction, since you are working with radioactive nanoparticles, okay?
Sure. Professor Half, I will include it as you suggested.
Okay, it's just a suggestion. Thelma, please feel free to accept or not, okay?
Good, that's fine.
Human also, please feel free, it's just suggestion. I have one doubt in your topic 221, electron range, okay, of your thesis. Why do you decide to get 1 up to 50 kV?
Yes, Professor Half, the reason was Actually, we had two papers working on parallel. So we were already considering 50 to 3 MeV already in another paper. So we wanted to have the complete range. And another reason is that 1 to 50 keV actually is the only point where the difference between the Monte Carlo chords was seen, actually. And the dose point kernels were only varying between 1 to 50 keV, so that was the main reason. And the other reason was like we had two parallel papers going, so we didn't want it to overlap the things. So we wanted one thing separate and another separate.
Okay, understand. Okay. Now, in your presentation, I think if you could come to your slide number 9.
Yeah, sure.
Tiago told something, and I think that I have the same point, but I have one doubt. Okay?
Yep.
Please correct me if I'm wrong, because I understand this way. In this slide, you are telling me that OG electrons are for cells, alpha, beta are for metastasis, and beta particles are from bulk tumors, isn't it? Is that correct or no?
Yeah, Professor, you can say that. If my point was like, if the radiopharmaceutical is uniformly distributed within the tumor, then Auger emitters are the best. They do not cause any damage outside the cell. So all they deposit, if they deposit the complete dose inside the nucleus, then they are the best choice. However, it doesn't happen like this. As whatever I have studied, there is always non-uniform distribution of radionuclides. In that case, alpha emitters and beta emitters come into play. But one thing I would like to point is like beta emitters cannot be used at the single cell level, at least not the medium and high energy beta emitters, because they will deposit most of their energy out of the cell, as you see in the DPK. I show just a second. Yeah. So if you see this, what is happening is the peak is shifting. Means the energy is not deposited near the origin. They deposit maximum energy away from their origin. So more energetic the electron will be, the maximum energy will be shifted. And they will deposit all their energy outside the cell. So at the cellular level, the high and medium beta emitters are not suitable. That's what literature also states that. However, Auger emitters are more suitable at the cellular level. So yes, you can say that.
Okay, but why you assume the metastasis point? That was I was thinking, because you are assuming that the metastasis is smaller than the bulk tumor, isn't it?
Yeah, my assumption is there are three things. One is micrometastasis, that can be just a single cell or maybe two cells or a cluster of 3-4 cells. But by metastasis, I mean maybe 10 or 100 cell cluster.
Yeah, but here in clinical, what I see is metastasis that can be bigger than the bulk tumor. Okay.
Okay.
If you have a breast, for example, you have a prostate cancer, okay, and you do operation and you do a resection of this tumor, okay. In the second wave of this tumor, this will be, of course, partially in the prostate, and the tumor, the metastasis will be in bone or lung or intestine, but it can be bigger than the real bulk tumor. So I don't think that the imaging in this slide is quite good for your presentation. You have done a very good work, and for me, this image is just confusing. Okay.
Yeah, sure, Dr. Huff. I will have a look and I'll study more. And if you have more suggestions, can you please send me some articles or anything, whatever you want to suggest by email? I would love to read and correct it accordingly.
I think like probably like what Ralph is trying to say is that like that you should basically separate like as you stated on the dosimetry you have the source and you have the target.
Yeah, I
Dosimetry is true when the source and target are the same.
Same,
But
right.
in the real clinical world, that is never the case.
Exactly.
That's the case in terms of the organ being irradiated on the organ. But like in the real case, you never have like you can never deliver all your radiopharmaceutical to all the cells. You will deliver it to some, and then these cells will self-irradiate and also irradiate the others. I think like maybe that's what is the point that Ralph is trying to say.
Yes, and since I understand that the qualification process is the process where you improve the quality of your thesis for the final presentation.
Yeah,
So
sure.
if you could change or assume another type of cells or metastasis bulk, something like that, I really think I really remove the metastasis process of your slides and put cells or tumor and bulk tumors. Okay, because the tumor one is a very small one and the bulk can be all the organ dominated by the tumor. But metastasis is a very complicated process, and putting here, I don't know if it's clear for the public that is assisting you, if it's really clear your message, okay? But as I told you, it's just a suggestion, okay?
Sure, Dr. Huff. I will resolve that issue as well.
Balli, please go to your slide 27, please.
Yes,
Just to point out about this picture, Half, it's not even his picture. It's
No,
for someone else.
I really understand that he took it from
A reference.
from an article, but sometimes the article has an intention, and when you put the figure in your presentation,
That's
the sense
yeah.
is not the same.
Yeah,
Okay.
that's true. Okay, thank you to point it out.
Balli, I was wondering why you didn't calculate the DPK curves for gold 198.
Actually, I have, Professor Huff, I have them. I can show you. Just a second.
So you are just keeping for you and for the thesis. Isn't it?
Sure.
It's a surprise.
No, I actually,
I was
it
thinking
was,
about that.
He's already working on his postdoc.
Yeah, of course. You want to have something new for the final presentation.
Or maybe the results were not so good. Let's hide it, So I'm not putting it.
Actually, Dr. Huff, it was reviewers pointed this out and they wanted to me to do calculations, and I have the reviewer report where I added these things, and so I'll just as soon as it opens, I'll show. I have both for all three of this platinum, gold, and samarium 153.
Okay. No, because if you have already have, and one of the points of your qualification and thesis is the gold nanoparticle, I really think that you should put in your presentation, or you should have put in your presentation, okay?
Yeah, sure, Dr. Huff, I will do that.
Because as Thiago has told, and also Mauro, and I think that everyone has told, you have done a lot of work, and for us that are reading this without your scope of view, we have to understand what you are doing now and in the next paper, in the next paper, and in the next one, because we have to create a history in our head to truly understand the whole complexity of your work. So making the highlights, as one of the reviewers here have already said, I think that's very good. I really think that if you could bring in your presentation the highlights of the first topic, the second topic, the third topic, will make it clear for us to understand what you are telling us and what and where you are trying to get with this, okay? But if you have calculated, okay, because I really missed the information about the gold, because you have been working with gold, and when you show when you show it, the DK, I was, where is the gold one? So okay, you have calculated this one.
Just a second, Dr. Huff, I have it
No,
here.
okay,
in
no
this-
problem.
Yeah, it's here. This is, is it visible?
No, not yet. Maybe if you stop the presentation and open it again,
Yeah,
it would
sure.
be easy. I think.
Sorry.
That's fine.
No, relax, buddy.
This is
We are in
from.
home.
Yes.
most of us are in home. I don't think that Thiago and Bruno are in home, but I am in home.
Don't worry, on the real defense will be much worse. They can
Thiago
relax.
cannot complain. He is in Switzerland. He is very good. So don't complain.
Don't
It's almost my sleeping time.
Oh, that's true. Poor Tiago.
So this is what I got.
Okay.
And not only this, I have also calculated these things. The radial energy, if it is uniformly
The
distributed
radial.
within the tumor.
Okay.
So in case of platinum, we assume that there will be no dose going out of the tumor. But in case of the gold 198, we expect that the dose is going to go out.
We have influence. Okay.
So
Okay.
I have
And the DPK.
Thank you, Bali. Bali, I have another question. And sorry if I have so many questions because I'm a pharmacist, so I'm really in doubt with some points.
That's
sure.
really good. That's really good. I like
In
it.
your presentation, slide number 50.
yes.
You have the survival. Okay. Okay.
Yeah.
You have the survival fraction curves for tumor size. Okay.
Yes. Mhm.
And I was thinking, okay, the main issue that we have with nanoparticle is the high accumulation in liver and spleen, okay? Because it's the mononuclear system, because it gets everything, it's prepared to do this, okay? I can observe something like that in healthy cells or no? I can assume that the radiation can be as potent to kill the cell as for the tumor in healthy cells. Do you understand my point?
You mean like we are directing the nanoparticles to kill the tumor, but it can also kill the
Non-healthy cells, exactly.
Yeah, of course.
Especially when accumulated in an organ like liver or spleen.
Yes, I agree with your point, Professor Dr. Huff. Actually, the thing is, it depends on the nanoparticle size, actually. Like what I have read in the literature is, of course, you have an experimental experience that is much more than what I have read in the literature. But what I have read is that if the nanoparticle size is less than 25 to 30 nanometers, it is easy that they get excreted out of the body without damaging the normal tissues and cells. That's why they are sent as a cluster with the help of liposomes, and they are directly injected intratumorally inside the tumors, so that they don't have to travel through the whole body and give non-targeted radiation to the normal tissues, so that they directly enter into the tumor, and then when they get out of the liposomes or get out of the binding or carrier molecule, they get excreted out of the body.
No, I understand. Oh, no, I understand that we have small nanoparticles are easier cleared from the body than the big ones. Okay, but just very small nanoparticles. When I'm telling about small nanoparticles, I'm telling nanoparticles about 10 nanometers, 15 nanometers. Nanoparticles with 20, 30, 50 to 100 nanometers, it's trapped in the liver and the spleen, okay? And even the ones that are very rapidly excreted from the body, it stay a very long term in the kidneys, okay? Because the kidneys process is not so fast as we think, because you have the reabsorption of many of the nanoparticles in the kidneys excretion process. So I was wondering, because here, for example, in your relative tumor size and figure B, okay? The figure 1, the figure A, I didn't understand the scale, because it starts in less 7 and then become 0 and 7 and 14. What means the minus 7 days?
Oh, sorry. I'm really sorry about this. Actually, it is. We have mentioned this in the manuscript, but here I didn't explain. It's my fault. 0 means the day when the tumor, when the radioactive injection of the nanoparticle was injected within the mice models. So in the case of Mariam et al., they first measured the tumor size on -7. That is the 1 week before injecting the radioactive nanoparticle. So -7 means the day before injection. So they kept 0 as the day of injection.
Okay, understand.
And
okay, but my point is, for example, in your figure B, okay, you inject it in day 4, isn't it?
Yeah, they measured the tumor volume on day 3 and they injected on day 4.
Yeah, but you are assuming that your nanoparticle will be in the organ for almost 20 days, isn't it?
Yes.
Yes. Okay. So okay. So okay, talk.
We are just assuming that the consideration assumption we are using here is that the nanoparticles are totally confined in the tumor, and then they stay forever in the tumor and die within the tumor. Of course, it's not a correct assumption. But for dosimetry, we cannot change our. In this case, we haven't modeled that thing that to take care of that uptake and washout of nanoparticle, we already defined 2 parameters. One is uptake parameter and the washout parameter that is taking care of that thing. So here we are just assuming the tumor, that the nanoparticles are staying there up to 18 days, and there is a washout rate already included in our cell survival fraction equation. So yes, we are considering the washout of the nanoparticles as well.
Okay, but you are considering a specific time for washout.
No, Professor Half, it is not like that. As I showed here, this is the methodology to estimate. Let's say we have a pharmacokinetic data. I show you from, let's say, Kathy et al. If I have opened, yes, we have. Okay, so we have percentage average dose, and it shows for different time. Let's say it is 30 minutes, 1 hour, 2 hour, 4 hour, 24 hours. So we have actually 5 points. So I took these points, and there is standard deviation. Considering that, I plotted those points here on the graph.
Okay.
And then I tried to use a hit and trial method to come up with the mono-exponential uptake and washout function using this function, and used hit and trial values. And once I got the uptake and washout value, like uptake will be like within hour or few minutes, and let's say 10 minutes or 15, and washout takes more time. Once I had these values were taken care by in the equation.
Okay. So return to your in your page 50.
Yes.
Just to understand. Okay, so you assume an alpha is the big one, so you have 91 days and 50. Okay, understand. Okay. But just to understand and really to understand, okay? For example, you injected in day 0, okay?
Mm-hmm.
And in day 4 you start to see the tumor size, okay? During the process, of course, you have depression of the nanoparticle. Many of the radioactive material, or the radioisotope, I don't know how you call, but most of the radioactive material are in the tumor. But when you start to kill the cells, of course, what was in these cells is start to get out of the tumor. And
Yes.
we have this, some part of this coupled with the cells, okay? And we are accumulating this in the liver, or in the spleen, or even in the kidneys, okay? So it's possible to us to have a survival interaction in healthy cells in these organs with the use of these nanoparticles.
Yes, Professor, but it's a really complicated process. If we have a pharmacokinetic data of what is getting inside the healthy cells, maybe we can come up with the similar survival curves and show how much is the normal cell killed because of this radiation. But still, this is an analytical situation at this point. This can be a lot improved by, like, it doesn't consider these quadratic form of the dose, and also it do not consider other mechanisms as well. So I believe it can be improved, and still it can give us a rough idea about this normal cells getting killed if we have a pharmacokinetic data.
Okay, understand. Perfect.
How?
And my fala
If I may add something more in fact, this next work that Balli is proposing to do with the prostate phantom,
Okay.
there we will see more like the isodoses. After you include the nanoparticles in the prostate, and then we can have a picture of how the isodoses. One thing that we were wondering is we had this difficulty during this last month is to find research from the experimental part to perform this experiment to get us a percentage of nanoparticle that goes out. Is that possible? That would be one question for us because we are not experimental. So
Yeah, so
and
we don't have budget.
this is
Yeah,
one
for
thing.
example, what we assume as a nanoparticle in nuclear medicine that is used daily, okay? Albumin macroaggregate, okay? We can use this every single day for lung tumor or for lung function, okay? And this is a type of nanoparticles, okay? Of course, here in Brazil, we have a serious problem with the albumin macroaggregate doing the size, because our macroaggregate here can vary from 100 to 1,100 nanometers, okay? But in US, you have a near, not so broad, okay, range of size, okay? But this is experimental data that we can show you because we have this from the patient that we inject all the day,
Good.
every day, okay? And you have the fraction that is in the lung and the part that is in the kidneys, okay? And this is a operational data that you can get in every single hospital.
I see.
Even in Minas Gerais, you can get this. I really think that Marcelo can have a lot of this data because he worked with a long time with lung tumor, okay?
I see.
So
Okay.
I really think that you don't need something very specific for your nanoparticle, but with something that is nanoparticle-like and will help you to get something interesting, okay?
Good.
Sure,
Okay.
Dr.
And Bali, my last question I still have for you, okay? And I have, because I was very interested because this data is of crucial for us here in the hospital, okay? Of course, you are working with phantoms and with some box, with water, but we are working with patients and animals, and some things very, for us, is very interesting. So, have you thought to include the both data, for example, the survival fraction curve from the internal radiotherapy with radiopharmacy, coupled with the external beam radiotherapy, and try to see if it's really flat, this curve, and you have a very good therapeutic result or no?
Yes, Dr. Ahab, and that was the idea. Our idea was like to compare what happens in the external beam radiation therapy. Let's say we have like a few articles on that we perform dosimetry for prostate
Not
cancer.
comparing, but putting the both together.
Sure, that can be an idea that can be done, and we were that was initial plan was just to compare, but you are right. Like in the first slide I showed, the literature shows that if both can be joined, we expect to get better results. So sure, in future work we can consider that as one option,
Okay.
one idea to search or research.
Yeah, because for example, for me it sounds very interesting because if I can use the both techniques, one with intra nanoparticle and a coupled with an external beam, and this has a very good result, or not, for example, the internal dose has or suffer no influence for the external dose, and for the cancer there is no effect at all. So for us, I really think in the clinic, I'm just thinking in clinic. Okay, it sounds a very interesting data. Okay, so if you could okay, it's just as I told you in the beginning, it's just suggestions. Please feel free. Okay.
Sure. Actually, I'm also a clinical medical physicist, and I worked around 1.5 years there, so I can understand your curiosity because I was that same curious. How can we do this and that? So surely, we'll
Okay.
your points. Thank you.
Thank you. Thank you, Bali. Thank you, Selma. And was a very, very, very good work. And I think I have done, and I think everyone is happy with this.
Thank you very much, Dr. Hub, for your time and efforts.
Thank you, Gabriel. Very good. Thank you for your contribution. It was amazing for all of the contributions. We will keep holding. I'm just take notes here. We will look at all these points. That's very nice. So let's invite Dr. Bruno Mendes. If you still have anything, Bruno.
Yeah, that's a difficult.
Of course you have.
Let's try.
It's your floor.
Professor Tassi, do you want to speak first, as I am your student? You can speak if you want.
No problem. You can go ahead.
Okay. First, I would like to thank you, Professor Thelma and Bali, for the invitation to take part in this qualification meeting and take part in some of the works you do. I participate in some of them, and thank you for that. I would like to congratulate the other members of the thesis proposal defense. When you see such qualified members, it's a good indication that the work is good. Or the supervisor is crazy, but it's not the case. The work is good.
Or maybe both.
I'm not going to pay any drink for anybody else anymore.
But it's the first option, for sure. I want to say a few words about Bali because we work together. The time we worked together, he was a very dedicated student. He learned fast, and now he mastered 2 Monte codes, which is rare, not common for everybody, and very useful for cross validation. And sometimes some codes don't do things that other codes do, and so it's very important. In Brazil, in soccer, we can say Bali is kicking well with the both legs. And this time with Professor Thelma, Bali passes Professor Thelma, I think he learned a lot, and together I think they achieved very good number of publications and good journals. So I think the work is going well. About the qualification, you can be without fear, mainly in my opinion. Really,
Now you are getting rid of the fears that were you in depth.
okay. About the thesis proposal, I think there's not much left to say. The professors that talk first point the main suggestions to the work, I believe. One point I think everybody talk about is the most important the highlights of the work. And I think the last work, this self-survival work, is the highlight, in my opinion, because you use all the works you do. These previous works have important important data too, but this one is this last one, I believe, is the most important. About the manuscript, there are very few typing errors, and some suggestions I put in the PDF and file that I will send to you.
Good.
I think in the final version, you should include a list of abbreviations, because it's good to add it too. It's interesting.
Sure.
About the presentation, I think it was very fine. The time was fine too, and only recommend a little more passion for the work. But okay, it's fine. Only a suggestion. I have only one question that survived all this viewers. It's about the electron transport, because each time we want to simulate in smaller dimensions, and like a cell and DNA, and each time we will try to transport lower energy electrons. Okay? For you, what is the lowest energy that we can transport electrons safely? Because there's no validation results. What do you think? What's your feeling?
Well, Bruno, actually, I did this test, what you're talking about, in terms of S value. There are some data that is published in 2011 or 12 by Bosses et al. And Professor Mfitsiglu. I'm sorry if I can spell his name wrong. But there is a group in Sweden, Stockholm. They work on S values in spheres, and they have given, using their own Monte Carlo code for nanometer size spheres, and there the deviation was really high. As you go very small to the dimensions of the sphere, the S value starts showing terrible results. I even saw the differences as high as 100%. I don't exactly remember the name of the code they use, but I have that in the manuscript they have done, and I have provided a literature review. I think it's in the chapter 4, where I have provided a complete literature review on the S values. There have mentioned, maybe I haven't mentioned this limitation, but I think that both are should be taken into account, the energy as well as the size of the detector that we are considering. Both affects and about the lowest energy, according to genes for DNA, it can accurately simulate up to 7 electron volts. So I haven't worked in the nanodosimetry area right now, but sure, I hope to work with Professor Yan with this, like DNA damage, and then I would be really sure with my answer, and I'll answer you.
Okay, no, it's only a feeling, because when you look to the decay curves below 10 keV, that there is some discrepancy.
Yeah.
And I believe with lower energy,
everything fall apart.
And if you don't have the experimental results or other form to validate, maybe try to think something to validate these results. It's
Sure.
something to the future when taking bath.
Sure, Dr. Bruno. Actually, I think I mentioned this about with Dr. Thiago as well, that or Dr. Professor Haf. The thing is that the dimensions I have used are in micrometer, and even if you go to use the minimum as 1 keV, it travels just 1 nanometer is the range. So whatever results we have presented here, they have no impact with the, if we use a 7 electron volt as a cutoff, or if we use 7 electron volt or 1 keV. The results are not going to get affected in any way.
Okay, Balli, that's only
Thank you.
I saw that you used some automatically generated spectra. That's right.
Yes, we simulate. There is it is only possible with GN4 actually, and for X we have to go to NNDC website. We can select the complete decay or the average decay, and it uses that files from NNDC Brookhaven website. If there is no radionuclide available, you can go and get there. So that's why, because NNDC website is continuously updated. So that's what I found is better to use from there. But still, in our paper with in nanoparticle, recent paper where we calculated the cell survival curves, this thing happened there. The platinum 103 emission spectrum varies between what mud committee supplies and what is present on the NNDC website. So this variation also affects our dosimetry and limits our accuracy. So maybe we can, that's what I suggested in the final projects that can be done, is to come up with something that either we find the discrepancies and then try to solve them, or get something that can accurately simulate the decay.
Yeah, that's what I like to suggest you, is really that, for example, for alpha particles, your results are comparable with the reference value, but I think it's good to try to generate your own spectra and validate some cases, because I'm very suspicious with these automatically generated spectra. Sometimes they are specific for some application, and we use in other application the problem appears. So that's one suggestion I remember now to give here for you. I think you are, for finish, I think you are dominating the simulation world well, and in the future I think it will be very useful to you, to tell and to everybody in the group to find some cooperations with people that do websites, experiments, radiobiology experiments, and others like this to apply these tools that you are
Yeah.
well. So I think it's a suggestion for the future.
That's what I'm looking for, Bruno. If someone accepts me as a student exchange program student, I would love to work and get the experimental hands-on as well on this thing, and so that I can be the real expert of this dosimetry, as well as I know the experimental perspectives as well. So, but I really tried for it as well. But if I get it, definitely I'll improve that.
Well, I think it's a suggestion.
Yeah, sure.
Which we all can
Yeah.
work with this data. It will do it to everybody, I think.
Yeah.
I think that were my contributions. I would like again to thank you for the invitation and congratulations for your work. Okay.
Yeah. Thank you, Bruno.
Thank you, Bruno.
Thank you for all your support, man.
Thank you very much. Good contribution. I thought you would say you have to find some rich collaboration to provide us a good laboratory. You know, it's like to do the experiment and
When the
apply,
lights off, I say
and apply all these proposed things. We have a methodology. Sometimes it's missing in literature, but
the link with
this talk, because of that, I invited Professor Half. He knows all the experiment on this topic. For us, it's really interesting to have feedback on this. This is really applied in clinical case, how we can make it a methodology that could be useful for in clinical case. And we need more this exchange experience. Yeah. For this, there is one curve here, but we can discuss about that afterwards. Let me, otherwise I will speak a lot here. We still have Professor Tarcísio, and then Professor Jan can contribute. Thank you, Bruno. Thank you very much. Yes. Okay, Professor Tarcísio.
Thelma, would you like to call the other professor first?
It's up to you. Normally, it's you. Do you want to be the last? Professor Jan, do you prefer to say anything? It's up to you, both.
You mean me?
Yes.
Sorry, I didn't. Yeah, I mean, a lot of stuff has been said. I think so long ago now that I forgot what we were talking about. Yes, I think as I said before, I think you did a lot of great work. So really, you have a lot of results to show. The one thing I would really advise you for your final presentation is put a timer next to you, just so you stay in the time. It's we're all okay here, but it's something you should practice. It'll help you. I have a few comments on potential future work and so on. I think the general question I had was, what do you think are effects of the heterogeneities? Because you talked about heterogeneities in different levels, but you mentioned them in the introduction, but you didn't really discuss them much in any of your results. So maybe you could either, in your next studies, include those, or talk about them more. Is there anything? Do you want to comment on that shortly, maybe?
Sure, Professor. You're right. I haven't included. The only slide was here where I mentioned that the heterogeneity is caused by absence of the blood vessels that limit the transport of radiopharmaceuticals within the tumor, and which causes the non-homogeneous distribution. Yeah, sorry. And the other, I got it. Sorry. The heterogeneity. What I meant was the heterogeneity, the difference in the tissue type. Like, for example, we have ear, bone, and blood, let's say, the three tissues. And these are the analytical solutions what we used, like the Voxel-S-Valley approach and the kernel convolution approach, where we assumed uniform water medium. But in reality, that's what we are going to consider in our prostate phantom. There we have segmented the bones, ear, like bladder, and we have also segmented different tissues. So hopefully we will be able to contribute about the heterogeneity and the differences in those distribution there. But since there is no air, so maybe we will not be able to go to the great extent. But maybe next time we can come up with a lung phantom, and then we'll perform that simulation too.
Yes, you already touched on two different heterogeneities there. There's the
Yeah.
other one on the cell level, right?
Yes.
Where you have heterogeneity in uptake of the cell. It's not only that you have it with different distributions in different parts of the cell, but you also
Yes.
have, due to what you just said,
Yes.
very different uptake of radiopharmaceutical in each cell, right?
Yes.
So
Yeah.
what you've been doing so far is kind of these averages. So yeah, I think getting to the, as you mentioned in the future outlook, also the stochastical analysis, that may be, well, I find those things quite interesting.
Sure, we are going to work together then.
Yes. Yeah, and I know I can tell you many things later, so I don't want to take too much time. I think a few things I would touch upon. I think the general accuracy of what you're doing is always going to be very limited by the data you have or anyone has, the physics cross-section, anything like that, and they are just, yeah, they're you know, you can't do much about it unless you want to spend another PhD just working on one cross-section or something. Yeah, so those are just things that I always find interesting to just keep in mind, because those are why you do get results that can fit very well, and you have, you know, you always have some parameters that you work with to make your results somewhat fit. It's important to, I think, remember how big your uncertainties are. Yeah. What did I say here? That kind of all touches on the same things. I think the discussion on your, of course, you're focusing on tumor tissue, and your what's called critical time is dependent on all these other factors like the uptake, the washout, and the half-life of the radionuclide you have. I think that could be explained a little bit better. I mean, I know what you said and what you're talking about, but I think it might just be helpful to explain it a little, just clear how those depend on each other and how it relates to like a real scenario where you don't just look at this artificial tumor, but you look at a whole body where you have neighboring tumor tissues and so on, and you have potential sites. I fully agree with the discussion on site 9, so we'll leave it at that. I'll give you a few more comments on the thesis as well, but I think we've talked for a long time already, so I'm just going to stop here, and we'll meet a few more times, so I can give you more advice then. Overall, as I said before, I think you did the amazing amount of work. It will help you to make it much more clear at the beginning what your achievements are, as everyone said. But yes,
Thank you very much.
Thank you, Professor Jan.
So big questions are about to arrive.
No, come on. I mean, I'll be shocked.
No, Professor.
Yeah. Let's start.
Yeah, sure.
Well, Balli, about your title, I suggest you think about it, because it's better say what you did, you first did by yourself, and the complementary work you can just say correlated research, like
if you did the S-value calculation, you call S-value calculation correlated work. Like your time will be restricted and more directed to your work that you've done. Okay? Indeed, the work, the title as it is now, target radiation therapy and nanobrachytherapy, as you define, nanobrachytherapy is a type of target radiation therapy. All the same, are all the same. So you can remove the one of the subtypes. Also, nanobrachytherapy, I'm not sure if it's using in the literature, but in my opinion is wrong, because brachytherapy is a therapy. You have teletherapy, brachytherapy, and systemic therapy. And nanoparticles are enclosed in systemic therapy, like radioimmunotherapy and other molecular target therapy. So nanobrachytherapy is quite strange, because I know that brachytherapy in Greek is near therapy of near targets, but brachytherapy is not systemic, and nanoparticles are systemic, needs to be systemic, including nanoparticle therapy. Doses sometimes is greater in liver, in red marrow, and spleen, as Professor Gabriel tells us, sometimes not in the tumor. So brachytherapy, it's because I say nanobrachytherapy is not a concept well defined.
That sees you. I was wondering, because sometimes, okay, we use the nanoparticle as a seed for the tumor. We inject into the tumor, not in the systemic way. For example, I do a X-ray or a CT mostly, okay, and then I inject the nanoparticle in the tumor, direct in the tumor, okay, guided by the X-ray or the CT, and in this time I don't have a systemic development of this therapy, and I really think that Balli may be thinking in this type of nanoparticle of this therapy, because for example, especially for good nanoparticles that don't have any specific target for tumor, so we have to use direct into the tumor, okay?
Okay, but if you do apply in locus nanoparticles, maybe it's experimental done, but clinically, I'm not sure, because if you have one of the problems of applying iodine 125 seeds is that in the prostate, is that the iodine seeds dislocate and go to the brain, like you have a wash of the seed out of the tumor and go out of the tumor in other organs, going to other organs. In this case, if you do nanoparticle by applying directly on the tumor, for sure you have 9% of the particles go further, like wash out. So I'm not sure if brachytherapy will be a good concept. You must think about, okay? If the literature supports you, that's fine. But if you don't have supporting from literature, you can think about.
Well, Professor, in my answer, I would like to mention that first you talk about the clinical trials of using radioactive nanoparticles. Yes, Professor Halp is right. I have considered by nanobrachytherapy, I mean intratumoral delivery. That is, we are directly injecting the tumor's nanoparticle within the tumor, and that is what in our cell survival fraction paper, we have considered only those cases where the nanoparticles were intratumorally delivered. And yes, you are right that there are systemic therapies with nanoparticles, but there is a defined term, this nanobrachytherapy, which has been developed in recent years. And there are many articles from Katie et al., the group from Missouri, our collaborator, and there is Professor Andemar Lugão from IPE in Sao Paulo. They are organizing phase 0 trials, I think, somewhere in a hospital in Sao Paulo. And there are some phase 0 trials on these radioactive nanoparticles going on in India as well, because they couldn't get the approval in US, so they started in Brazil and India. So there are phase 0 trials, and they are going on the same name, nanobrachytherapy or anti-tumor therapy. We're using radioactive nanoparticles.
Well, okay. I have some concern about this type of application, because if you already assume that you need to apply directly on the tumor, you need to first know that you need to know where is the tumor. So you are not going to apply it in metastasis.
Yeah, sure.
Also, if you are doing directly, it's because your selectivity is not well defined. Like if you go to the stem therapy, the nanoparticle must be glued with a target molecule to go to this cancer cell. And so it's, I'm not sure if it's go further with direct application.
Well, Professor, in this also they use carrier molecules that target the receptors or antigens that are overexpressed by the tumor cell. For instance, the group from Missouri that I talked about, they have developed the target with the name mangifrine. It is developed from the mango leaves of mango fruit, and that targets the ligand that is particularly, I forgot the name, it was just there, but the ligand that is particularly overexpressed by the prostate cancer cells. And yes, you are right. These are not for the metastasis, as I mentioned before, that nanoparticles can carry thousands of radioactive atoms with them. So that means they are planning to use them to treat solid tumors, not the metastasis. The aim is not to treat the metastasis. Aim is to treat the solid tumors with minimum radiation to the normal tissue. Like in the case of prostate cancer, even if we do the VMAT or IMRT, still there is a lot of dose that goes to the nearby normal tissue, and we cannot do anything about it. And so this is the idea to use it as a nanoparticle, as a nanobrachytherapy, what they call it.
Okay, I think it's a good idea also talk about the radioimmunotherapy, because radioimmunotherapy is a target therapy, adjacent therapy, and in your text in the chapter 1, you call indirectly, you tell indirect about this technique, because you did target antigen selection, okay, 113. Actually, antigen and target antigens for immunotherapy, radioimmunotherapy. So, and you not mention these words, you just mention DRT. So maybe you can increase it. Okay. Actually, it would be good to tell you to know the history of radioimmunotherapy, because radioimmunotherapy did the same as a nanoparticle therapy, like the same problems that you have in radioimmunotherapy, you are going to have in nanoparticles. Okay? I think if you read about the history of this therapy, you will understand the difficulties that you're going to face in the future.
Sure, Professor. I will consider your comment and I will read and write about the history of radioimmunotherapy as well. In chapter 3 or 4, I think, we have written some things about radioimmunotherapy, that it's a form of targeted radiation therapy where antibodies are used as target, and we have defined like 4 parameters that are considered in targeted immunotherapy, like specificity, and 3 more, like 2 are mainly related to the antibodies and 2 are mainly related to the radionuclide. Just a second, I get it there. Here. So yes, we have talked about the specificity, universality, cytotoxic potency, and short range effects. So here I have talked about the radioimmunotherapy, but surely, as you said, I should put an introduction.
Introduction.
Yes. I will read it and I will elaborate this idea there.
And also, as I think other professor mentioned, you will be interesting to see in the introduction the toxic effects of nanoparticles. So what they know until now about the application of nanoparticles and the clinical results and the deaths on these clinical results. As you know, the better know what is wrong than what's good.
Sure, Professor. I will work on it and I will include a section particularly on the studies that are that study the toxic effects of or the clearance that are caused by the clearance of nanoparticles, and I will add a section to it.
I have other notes, but I will leave for you reading. Just as some more observation, when you calculate the S value, I miss some information about the cell, like some parameters like density, and composition that actually you give it on your software. Your codes require this parameter. So maybe you can write it on the uses. Okay? Because it's doubt, it's difficult to know if it's good or not, this parameter.
Sure, Professor. Actually, we have included these things in each article, and I felt like it would be wrong to repeat the same thing again and again in the manuscript. That's why I left the articles as it is, and just in the introduction I focused on more about how this targeted therapy works and what are nanoparticle uses. Okay, I will include in the introduction as you suggested. But in each article there is, of course, my presentation doesn't include that whatever cells we consider or media medium was always water. We didn't consider any high density material, it was only unit density water. So it was removed just because of the timer, like it was taking too long to present the whole things. And like as Professor Yen said, I should take care of time. So we were taking care of time and removing extra slides out of it, and still also I took extra 8 minutes. So sorry, but sure, I'll consider that.
Maybe some part of the code that explain what was the parameters used, and you added it as in an attached annexes or of the thesis. Just make sure that it's there. Good.
Yeah, sure.
Good point.
Okay. Other point is your cell model of growing based on actually start from quadratic model, survival of quadratic model, and you just use it as a parameter to multiply by the volume of the tumor to find the new volume of the tumor.
Yes.
So you made a work in survival fraction. However, in the tumor model, it's very weak. It's just multiplied by survival fraction volume. The volume is multiplied by the survival fraction. So, actually, if you want to maintain this way, better you say not you have a tumor, like you have a mass or a volume of cells, but not a tumor, because the model will not represent the tumor. So you must think about maybe change, because you're doing some modeling, cell modeling, growing, but not tumor growing. And also I saw some results. I'm not sure because I didn't have all data, but I have some results of survival fraction in value of 10 minus 14. A value is low, very low. Is it true? Can you get the figures?
Which one, Professor? You mean, is it in the presentation or is it in the...
I think it is Balli. Is the one of the CATIS, I think the slide 50.
Okay.
50. Oh.
Yes.
Page 50.
Yeah.
Is that one, Tarcísio?
It's, I think
No.
it's,
Go for the other
you mean
one.
this one.
Ah, that one.
Yeah.
The completely nonsense. 10 minus 50.
Well, Professor, I agree with you. Here, the point was to compare the therapeutic efficacy. Of course, 10 is minus 50 means 0. And there is nothing available. So, but in order to plot this comparison, we did it. But of course, practically or clinically, it means 0 or complete cure, that there is no tumor cells available, or it's over irradiating.
Actually, here I found some questions, because not questions, but something strange, because your tumor decreased almost to 0 in less than 1 day. Like very strange in radiobiology. So maybe actually you can do a graph in hours. Maybe you have this, but not going to 10 to minus 50. Maybe you go to 10 minus 5, like that, like 10 to minus Uh, but actually, maybe it's because your model, no?
Yes, Professor. Actually, we considered extremely small tumor size, that is 0.3 cc, and the energy emitted by this radionuclide is too high. So this model
Yes.
behaves like this. Otherwise, if you see the graph for platinum, it is not that strange. But in order to compare, we had to put it like this. So
Actually, your result is because of the energy that you are putting in a small volume,
yes,
like
exactly.
50, 40 or 60 megabecquerel is very high
Yes,
for a larger small volume.
yeah, and I totally agree with you.
Maybe you can reduce it to get a result more
Uh,
realistic.
I think we got this. Yes, for that we did this, Professor. In the case 3 and 4, this thing was considered where we varied the tumor volume and we assumed that all radionuclei result in same absorbed dose. So in that case, the radioactivity factor was adjusted, and it was found that gold and samarium need almost 600 like activity by less by factor of 600, like to deposit the same dose as platinum do. But you're right, like this is not doesn't make sense to put E 10 is power minus 50, but it is only the effect because we are comparing with OJ emitter, that is platinum, and which is causing this conflict here. Like if we compare the beta emitters only, we might not have gone to 10 is power minus 50, or we might have considered tumors of much larger size.
Because the good thing in your work is to show that a very small activity you get a good result in biological response,
Yeah.
right?
Yes,
Like
right.
a very small amount of megabecquerel inside of a cell gets you better results.
Yes, sure.
It's not showing here, like, because you go to 10 to the minus 14.
Yeah, sure.
Well, other questions, it's more a suggestion. It's like you show in the article and also in the introduction the description of the codes and that you have used. But one question that I understand the thing using AOB is how they treat the cross sections, the ionizing cross section for electrons, electronic ionizing cross sections in low energy, like 10 eV until 1 TeV, so or 10 TeV. So you may be found on the literature the cross sections and show it to us. So to see how is this cross section how it's vary with energy. Okay?
Sure, Professor. I think I will try to add it in the introduction, but like you said, in the presentation, we had to remove a lot of slides
Of course,
because of the time limit, so maybe we will not be able to include. If someone specially asks the question, I'll keep the slides ready for the next time.
Okay, because if you have the cross section, you can also add the mean free path of the electrons in the medium. So with the mean free path, you are going to compare with the size of the cell. So actually, with this data, you know which energy, how electron is transported inside of the cell.
Yeah,
And also, if you do this, you are going to observe that there are some energy that the particles go further and never touch your cell. Okay?
Yeah.
Actually, the S value doesn't mean anything for that energy.
Yeah, you are right, Professor. That thing we have shown about the gold 198 in our manuscript, wait, I show you. That thing is visible here. That's why we performed single cell dosimetry along with the cell survival. If you see this particular, let's say cell to cell, yes. If you see this, so here the maximum energy is deposited by samarium inside the cell when whole cell is considered as the source. Whereas when it comes to gold 198, it is depositing most of the energy outside the cell. And that's what I tried to show here also. If you see this, when we compare the platinum and the gold, so the most of the energy is getting out of the tumor or the cell.
No, actually, despite of that, they are using gold as nanoparticles, right?
Yes.
Gold
Yeah.
198, because they do not think for one cell, but the collective of cells receive those.
Yes,
But,
the crossfire effect.
so the concept of SS value for one cell doesn't mean anything, but if you do a collective distribution, maybe you find good results compared with the clinical stuff.
Yeah, I totally agree, Professor. Actually, the cellular S values are generally used to know the therapeutic efficacy of Auger emitters. Auger emitters does not travel the whole, even they just, as I showed here, they don't even go to the cytoplasm area. That is just 1 micrometer or 1 nanometer far. So that whatever you spread in nucleus stays in nucleus. So that's why the cellular S value arose. And there is a software that is called Merge Cell that is given by Merge Committee that can be used for cellular dosimetry, and it is widely used for this kind of cellular S value calculation as well as survival fraction curves estimation.
All right. Just more to finish on, like you are intent to make the macro dosimetry with prostate in phantom. It's a nice work and it's a good option. You can find good results, but they release out of your thesis, no? Because if you are doing microdosimetry, you are doing microdosimetry, now you are going to do phantom dosimetry.
You can say that, Professor. Of course, then if it gets out of the thesis, we can put it in appendix, but still it's a good work.
I consider the work you have done is very good.
So, idea is to do the work and research, Professor. Whether it stays in the thesis or it stays outside the thesis in appendix, work is work and it will give us publication. So important is we get a publication.
Yes, it's true. But the choice you let others not doing.
Yeah, sure. I agree, Professor. So maybe one. Yeah, sure, Bruno.
I forgot to tell this for you, but I think the prostate phantom can be a side project, and the radiochemistry study I think is more related. Maybe you should focus and
Or
this work, and if you have time, you do the phantom work.
Yeah, well, or you choose a systemic radiation therapy with prostate and do it in the prostate phantom. Like actually you can do with samarium. It's not samarium, it's radium. Radium
223.
Yeah, 223. Maybe you get a result that can include your thesis.
Well, Professor, the idea about using a prostate phantom was the phase 0 trials of Professor Getty and Professor Andemar from São Paulo and Missouri. They are our collaborator, and my idea was to come up with some kind of a treatment planning system or something that they can use in a prostate phantom. They know the activity and they can perform the calculations. It is the first time that we are using voxelized human phantom library of eggs. It was not ever used before, so it is using the nanobrachytherapy, as we are going to consider full nanoparticles here. And as long as the dosimetry of full nanoparticles for nanobrachytherapy stays, I think we can keep these results in thesis as well.
All right.
What do you say?
Well, you must justify, give a reason why you are doing phantom dosimetry inside a nanoparticle thesis. That's
Yeah, so our idea was to first get the radiation, what is getting out of the nanoparticle, and then use that radiation as a source inside this prostate phantom, like using a prostate as a target. So it will relate the nanobrachytherapy somehow, because we will have a radiation that comes out of the nanoparticles, and then we are using that radiation directly in the prostate, like we talk about the intratumoral injection. So it will be part of the thesis anyway, but if you think it is not, then we will add it to the appendix directly. No worries.
In fact, Professor Tarcísio, this was an idea from, I don't know, at the end of 2018?
Yes, and Professor Tetma didn't agree. So
yeah, I was like, no.
This kept us so long, otherwise we would have finished it very early. It was like I and Bruno working in the background and not telling her that we are doing it. And now when we have the results, we showed her, see, these are good results. And now she agreed that yes, these are good results, we will publish and it's a good work. So this is how it came out.
And the idea was Bruno teaches Balli how to manage, how to work with the segmented phantom, how to do it. And that was the case. And suddenly someone from Hokkaido, I think, university in Japan, developed a code for eggs to collect all the information, transform it in a binary file. It was something more like a computing thing, and prepare the phantom automatically. So that was the idea at that time. And I said, no, don't work with this now. Let's focus on the nano thing and the microdosimetry. But now, okay, they have the results. They want to publish it, and we can manage it. This can be something from 6 p.m. to 11 to him to do.
Yeah, so it was developed from my interest, and I never stopped working on my PhD, and she never had any complaint that I'm working too slow, so she never get to know that I'm working on it or not.
Yes.
All right. Well, for me it's fine. I finished, and I just would like to thank you. You have a good presentation, and your work is very impressive. A lot of work done. Congratulations.
Thank you, Professor.
You and Delma.
Thank you very much.
Thank you, Professor Tarcísio. You point out a lot of things really interesting. We have to discuss about this again. And for these last results that you're talking about, this minus 15, the relative size of the volume that we're talking about, the survive curve. This is the last work we've done, and we are about to publish it. Maybe that's the case to improve the methodology, how we consider the survive curve, and we put together the survive curve, something experimental, with the Monte Carlo calculation. That's the idea, in fact. So
actually, this survival curve thing also started in 2018, to be true. And we were searching for the experimental data, and at the end I had to digitize the published experimental data. I didn't have any other option.
now we have Professor Hall.
Now we can contact the Professor Huff.
And Professor Tarcísio as well. So
Yeah,
I mean,
his experience,
yeah.
we can get benefit from his experience.
yeah.
Probably.
But thank you all guys for the contribution. Is there anybody else who wants to point out anything, or not 50 questions anymore, but something?
Yeah, sure. I would like to thank three people especially here. One is, of course, my supervisor. To be true, I have friends almost all over the world doing PhD. And I was the coolest, like never pressure, never deadlines, never anything. Like when I first arrived, she came to the airport to pick me, and it was a great hospitality. And every party we went, she paid all my bills. So thanks, Professor.
I hope you paid the last one.
And the last thing is, I never faced any trouble with the work. Even I used to work late, and she will say that, come on, go home and have rest. You don't have to finish your PhD in 6 months. So it was really easy. She was friendly all the time, and working with her was really fun. And I never faced any trouble. Of course, we faced a lot of trouble from the department, but that's another thing. But with her, working was totally fluent and easy, and I was allowed to do work on the projects, and I was allowed to say what I feel and work. So that was perfectly cool. And the second is my co-supervisor, Professor Yan. I'm really grateful. He, even after every meeting we had, he will especially find time to point out where I was weak, and finding what is required from me and what I'm doing and where I'm lacking. So that also really helped me. I can feel how I have changed over past few months. Initially, I was really, like I said, there were many ideas that were started in 2018, but we couldn't finish. But the way he tell how to focus and what is lacking in me, I tried to put that focus, and the results were incredible. And you all can see in the terms of publication that we have got. So thanks to him, and I hope he will continuously keep sending me emails what he feels and where I can improve. And of course, I annoy him by sending wrong scheduling of the meeting and other things. I hope he will not mind that things. And the last person is Dr. Bruno. He always is like a elder brother to me. And he's, of course, almost 20 years elder than me, but he never makes me feel, and we talk almost about everything, research, problems, and all the things, and he is an amazing person. Thanks, Bruno. And since Johnny is also there, so thanks, Johnny.
Thank you, Balli, for your words. I will just, we have to do one second part of this this presentation. I have to invite all the Balli and all the other group. We need to stay only with the committee here now, and then we discussed about the results, how we feel like it's approved or not. We will decide, and then we can invite Walid back, and then we tell him the real results, what the committee wants to say, in fact, in one word. So I will ask to the guys to leave, please.
Me too.
Yes, sure.
So I'm kicked out.
I tell you by your WhatsApp.
Okay. So,
Okay? Yes.
how to leave the meeting. So,
Good.